Magnetism. Okay. Very
Okay.
good. Yes,
Okay, we're good.
we're good.
Okay, I should get more used to doing this, but it's okay. Yeah, this involves a model that I've been working on for a long time, to some extent with the help from Harry and a number of other people. About a month or maybe it was 2 months ago, I gave a presentation on the model's version of the electric field in terms of properties of thin shells, where the thin shells consist of ideal liquids, positive and negative ones, and where they each have equal volumes. And since they each have equal volumes, uh, their internal width varies at an inverse square rate. And so you can get the inverse square rate for the electric field pretty clearly right off of that, and then you just have a summation of the effects from the electric fields of various particles. And I have these layered together in a parallel 3D spaces in an overall 4D space. And the details are given in my ebook, A Model of the Physical World, at my website, www.quantumrealism.net. I'm always trying to improve things, and I should say I'm more confident, or maybe even considerably more confident, of the details of the model for the electric field than I am for magnetism. But I'd like to get clearer about magnetism, and hopefully some people can help me out a little bit in the process of today's meetings. Let's see, when I move on
Well,
to
I
the.
just want to comment a little bit. What magnetism is, a lot of people think that astronomy is one of the first sciences, but it turns out, based on my studies, that magnetism is pretty close. And it goes back to Thales and the Greeks. And so it's been around for a long time, and people have been speculating about what is the cause of magnetism for quite a long time. And I think this continues onward to the present day because Robert's going to talking about this issue. What is magnetism? What causes it? Still a
Okay,
mystery.
yeah, and I try to form some linkages here with spin and spin of the electron and also light polarization. And it's interesting, I come up with the same diagrams in terms of vortices and singularities at the poles in all three cases, which tells me that maybe there are at least close relationships among these. Okay, I think that the way I'd like to try to handle things is to go through the presentation and then open things up for discussion. A lot of this I know is speculative and controversial and any number of things, but I'd like to at least get through it the first time and then, as I was saying, open it up for discussion. Okay, so let's see.
Well, you're welcome to start.
Okay, here's my first slide, History of Spin. Okay, yeah, the first paper I know on at least the way spin is talked about in quantum mechanics. It goes back to a paper in Nature by Uhlenbach and Goldschmidt. They were Dutch. Interesting, Uhlenbach ended up at the University of Michigan. Uh, and they do not give a relativistic interpretation of spin, but they do talk about the spinning electron, and it has two states, spin up and spin down. And they,
Let me interrupt you here, Robert.
yeah,
According to relativity, magnetism is a relativistic effect.
uh, that part is true according to relativity. I don't think magnetism is a relativistic effect either.
Yeah, well,
Uh,
that was one of the things that caught my attention and caused me to look at what special relativity was about because of that claim magnetism is a relativistic effect. So,
yeah, I know. They say it's off the Lorentz contraction, and I don't think it is. But
Okay, but anyway, you mentioned that, and I just thought I'd comment on that.
sure.
That's a kind of a controversial concept, I think. I
Yeah, a
don't
lot of this is controversial. I'll be the first to
really.
admit that. But in any event, they account for the Zeeman effect. The Zeeman effect is a splitting of spectral lines in the presence of a magnetic field. And they do this in terms of whether the spin is spin up or spin down. You get different energy levels there, and that they say that accounts for the splitting of the Z-man effect. There's also something known as a G factor, which is related to the gyromagnetic ratio, the ratio between the magnitude.
Bob,
What's that?
Bob, could you explain what the Zeeman effect is?
Okay, the Zeeman effect is a
That's when
splitting
you
of
apply a
spectrum.
magnetic field to an atom, to atoms, right?
That's right. And it's a splitting of spectral lines. And there's the normal Zeeman effect, where it's just a single splitting, and the anomalous Zeeman effect that has even more splitting. And for the normal one, it only occurs for atoms with even numbers of electrons. I guess maybe the effects cancel out for odd numbers. Uh, but in any event, they also talk about where the spin angular momentum is twice that of the magnetic angular momentum. This is known as the G factor, uh, which is related to the gyromagnetic ratio, the ratio between angular momentum and magnetic momentum. Uh, the Landé G formula I give at the bottom here, where J is the total angular momentum, S is the spin, L is the orbital angular momentum. And Dirac, he claimed that G equals 2 is a relativistic effect, and he gives a derivation, which I've never been able to follow. But it seems like modern quantum mechanics, they all went along with Dirac's interpretation here. But the only point I want to kind of emphasize is that it was not Dirac who came up originally with spin, and that the original version doesn't bring in special relativity. It just talks about a spinning electron. Okay, let's see. Now I start to show these isomorphisms, in other words, similar structures between spin, light polarization, and magnetism. First, for light polarization, yeah, it was Henri Poincaré who came up with what's known as the Poincaré sphere for different polarization states. And you can either do this for an HV basis, for horizontal and vertical polarization states, or you can do it for what's known as the helicity basis for circular polarization, either right polarization or, excuse me, clockwise polarization or counterclockwise polarization, where those are given at the poles. And for intermediate directions, those correspond to elliptical polarization. And in my model, I take this quite literally, where with my spheres, when I identify light with transverse waves propagating outwards from an emitting particle, where these spheres oscillate. They can either oscillate horizontally or vertically. And there's also a way you can get circular polarization here, which I show in my next slide. And this is the one where I keep coming across this same diagram for light polarization, for spin, and for magnetism. And the basic idea here is within a thin shell, if you have the same rectilinear velocity uh, throughout the shell, first off, you're going to get singularities at the poles. Uh, and as you go up, you'll get these little eddies, and they'll rotate in opposite directions, whether you are above the horizon or, excuse me, not the horizon, but the equator, or below the equator. And these eddies, as you can see, they'd have to spin essentially an infinite amount at the poles. So something breaks down at the poles, which is a good question. But for the HV basis, okay, there you just get these macroscopic motions back and forth. But with the helicity, there you can do it in terms of these eddies. Okay, in other words, helicity, okay, those are these little rotations. So that's the polarization for the circular polarization. So you can build it up either way. And as for which is fundamental, well, there's actually a debate in the literature, and it seems you can actually do things either way. But that's for the case of light. Okay, now I want to move on to spin. Okay, I found this book. I've had it for a long time, by Hertzberg, Atomic Spectra and Atomic Structure. And it's a real good little book for explaining uh, spectra, and it doesn't particularly bring in special relativity or anything.
Okay,
But
this is a book that's a Dover book. It's a paperback Dover book, as I recall.
that's right. And I found it very useful
Yeah.
because it goes into the details and you can follow the details. So here you have, like, see, you have an electron precession. So there's a shift away from the polar position. And here the spin vector is twice as long as the one for the magnetic one. And you do a summation between the orbital, the L, and the spin one for the J, where the J is the total one. Let's see, the next one. Account of spin in terms of vorticity. Okay, I actually came up with the diagram on the right, and things actually fit here pretty nicely, which seemed to me as some evidence that maybe what I was saying was on the right track. And so here we have a magnetic field, and spin properties only come into that we observe, like with the Zeeman effect, in the presence of a magnetic field. I mean, there's other evidence for spin, like with Pauli exclusion principle, where you have two electrons can be in the same state when they have opposite spins. So you do need an additional degree of freedom, an additional a quantum number there. Uh, but in any event, here you can talk about the component of the electron's magnetic moment in the direction of the magnetic field. So here it's related to the cosine. And when you add things up here, where you keep the constant rectilinear velocity, as you can see, the spin one comes up twice as high as, let's say, the position D here, and the resultant is the J, the total angular velocity. So for the unit circle, AB equals CD, that's the linear velocity, then that's equals the cosine of the angle, and then BE equals 2BD. So there's your G factor of 2. Okay, vorticity is, it's a vector. Feynman gives a good account of it, but, and Feynman points out that it's twice the rectilinear velocity, like he talks about as spinning a bucket of water. He says if you look at the rate at which things actually rotate, it's twice the actual rectilinear velocity, like with a spinning bucket of water. And I think that's related to why the G factor is 2, because spin is connected with the vorticity. Okay, so yeah, here I come up with the same diagram, except for the case of comparing this with the case of polarization. Polarization is light being propagated out through my thin shells. For spin, it's a property of electrons. And in my book, I actually have a whole chapter on this, a model of electron orbitals, which I have as being spaced integrally, so they don't die off at an inverse square rate. Actually, between shells for different quantum numbers, that goes R squared. For a long time, I didn't believe that, but it actually turns out the model works better if that is the case, which results in some pretty enormous atoms. And actually, there's some evidence for enormous atoms in deep outer space. You end up with spectral lines, for like example, with hydrogen that you don't get terrestrially. It turns out there's an interesting literature on that. So I take all of this literally. So you have these electrons. Now, I tend to identify electron. I definitely don't think of an electron as being a point particle. I don't like point particles. I don't think photons are point particles, and I don't think electrons are point particles. I tend to think of them as actually being spread out over an orbital, but you can have two electrons in an orbital when, as we saw with the Pauli exclusion principle, they have opposite spins, spin up and spin down. And hence the vorticity is going to be in different directions, depending upon whether you are above the equator or below it. So the diagram's the same here, even though what it's a diagram for, in this case, an electron orbital, is different from the case of light, a wave being propagated through a series of thin shells. Okay, and here's the case for magnetism. I'd like to have this worked out better, but it's a nice idea to try to have here is to have the north pole of a magnet be the case like with circular polarization, where you deal with one of these singularities, spinning like clockwise for your north pole and spinning counterclockwise for your south pole and for intermediary positions. And here I talk about this as the result of like the thin shells of one atom passing by the thin shells of another atom. So you get an interaction, at least with the other particle. And this results with these arrows here, the rectilinear velocity of a thin shell of the other particle, resulting in these eddies again, where they're clockwise above the equator and counterclockwise below the equator. Okay, which shows that, again, that there's the same structure involved for magnetism, light polarization, and for spin. Let's see my next slide. Isomorphisms among the diagrams for polarization, spin, and magnetism. Singularities of the poles correspond to
Robert,
the... What's that?
what's isomorphism? Explain that to
Same
me.
structure.
Okay, means the same form, basically.
Yeah, iso is Greek for same form, right? Same form or same structure. Okay.
I'm waiting for my watch to charge yet. Well,
okay.
Because I was dead during the night, so I'm waiting to get most charge before I put it on.
Hey, Cornelius.
All right, go ahead.
Well, I probably could do without it during breakfast.
Okay.
Cornelius, mute yourself. Mute.
Oh, sorry, I thought I was.
Yeah. Okay, so we have these isomorphisms. Okay, sameness of structure among the diagrams for light polarization, electron spin, and magnetism. Okay, singularities of the poles correspond to the north and south magnetic poles. Clockwise and counterclockwise circular polarization for the case of light, and spin up and spin down states for spin. Okay, above and below the equators, the eddies rotate in opposite directions, either clockwise or counterclockwise. These isomorphisms suggest that the same basic mechanism is responsible for each of the phenomena. Uh, that is, in terms of the constant rectilinear velocity of ideal liquids in thin shells or the electron orbitals here. That word phenomena, as far as I can see, it's due to Niels Bohr, and there's always been a debate on it. There's something that you observe. Some people press it into your actual visual sensations, and I don't think you have to go that far. But it's something that's sort of macroscopic that even a camera can register. So I don't think it has anything to do with consciousness, but it is something actually existing that is observable. But in any event, I also say that macroscopic magnetostatic phenomena, in other words, like with a single bar magnet, for example, where opposite poles attract and the same poles repel, are accounted for in terms of the alignments of the magnetic moments of their various components. So you have this internal structure, and when you do, like, if you stroke a piece of iron with a magnet, it becomes magnetized. So what the net effect is, you are changing the alignment of the internal structure of these individual atoms so that the magnetic moments become aligned. Or you can do the same thing like with an electric coil around a bar of iron. You can either magnetize it or demagnetize it. And in terms, again, it's in terms of the alignment of this microscopic structure that accounts for the macroscopic effects. Role of vorticity in these phenomena. Even though Feynman likes special relativity, I like a lot of what Feynman has to say anyways. I like what he has to say on light. There's light taking all possible paths. Only I interpret that as taking all physical possible paths. So my photons, they get split up and recombined and all sorts of things. But he also has a section where in his second volume of the Feynman lectures, where he talks about vorticity, and he says the local vorticity, I think I already mentioned this, is twice that of the rectilinear velocity of a liquid, and where he gives the example of a spinning bucket of water, where you put like a small piece of paper or something, you can then see the rate at which it rotates. And so this accounts for the G factor being 2 if you identify spin with the vorticity. So it suggests identifying the spin vector with the vorticity vector and the rectilinear velocity with the internal electron orbital velocity. Okay, speculations about implications for a model of magnetism. Okay, I've had a correspondence with this Jean de Clement. Unfortunately, he's getting quite elderly. I think he's in his mid-80s now. He's French, and he used to be a professor of, I believe, hydrodynamics at a university in France. It's interesting. At our meeting yesterday on emission theories with Harvey Slobodan Netic, I guess some of you know him. He said that he'd also had a correspondence with Jean de Clement, and he was interested in this same experiment that Clement talks about. Whether Clement is right or not, I don't know here, but it would be interesting if he is right. and that is in saying that the magnetic field just consists of the intrinsic magnetic moments of electrons and is not due to the motions of electrons and electronic beams. Now, there's some connection, obviously, between the movement of free electrons and magnetism. Like you get an old television set, obviously changing the magnetic field, well, it causes a picture, so it causes deviation in your electron beams and the free electrons. But the Clement says that this is all just due to the intrinsic magnetic moments. In any event, he talks about a test. Unfortunately, he never succeeded in doing this particular experiment. He's told me in
Bob,
an e
Bob,
yeah,
let me interrupt you here.
yeah,
What he's
sure.
saying is that there's no magnetic field of the beam caused by the motion of the electrons, but that the magnetic field is caused by the individual electrons in the beam. Is that not?
That's my best understanding. And I'll admit I'm not super clear about this. I wish I was clearer on it. Uh, but that's what, as far as I can see, is what he's saying. And he actually told me how to get a hold of one of these Narva PR tubes. And he wants to have you have to mess with the tube a little bit. So you put something adjoint at right angles, and then you compare this, measuring the strength of the magnetic fields, both when the electron beams go straight down and when they're deviated at a right angle. And he says that this should result in different measurements, which would be an interesting test if you can make some sense out of this. And whether I want to go completely along with this or not, I'm not sure, but it sort of ties in with what I've been saying about magnetism. If you don't have to bring in anything else extraneous, that would at least be a simpler theory. So I am interested in trying to pursue this. Let's see.
We got 9 minutes.
Okay, well, yeah, here's my implications for cosmology, and this is my last slide.
Okay.
Okay. Yeah, Harry asked for me to make some tie-ins with cosmology. I don't know if I have anything particularly novel to say here, but I'm definitely interested in being a realist about fields, about the electric field, and to the extent that you can account for the magnetic field with the same thin shells that you're using for the uh, electric field, I think there's a lot to be said for it. As far as I can see, I mean, Einstein tried with his unified field theory to give an account of the electric field, and he never succeeded. People don't always emphasize that. He did somewhat better with gravity. It's hard for me to imagine that gravity is also fundamentally different. I'd love to show that it's just like a residual effect of the electric field. I've made some attempts there. It doesn't work out as nicely as I would like. Okay, but if these are the bases of what physically exists, and you're a realist about at least these, then there's no need to bring in esoteric phenomena, which relativists like to talk about, like black holes, dark matter, and dark energy. I mean, I don't want to be dogmatic in saying that none of these exist. I don't really see any good empirical evidence for the existence of any of them. So I'm kind of a skeptic about them. Also, I strongly favor more empirical tests for adjudicating between the merits of various models. And obviously, among dissidents, there are a lot of different models postulated. And what happens may be too much, I don't know. But it's almost like everyone has their own pet theory. And one reason there's not more progress is that everyone just hangs on to their theory almost no matter what. So if there's a way to run experiments to test among them with something that you can actually do in the laboratory, I think there's a lot to be said for it. Well, why don't I mention three? One, I actually did some work here with a Chinese professor at the University of Maryland, Baltimore County, on light entanglement, where the idea was to see whether entangled light involves something like an advanced wave linking various detectors. For a long time, he was going to do it there. He was starting to reach retirement age, but he actually had them do the experiment in China. It involved using Pockle cells, and the results, at least the way he interpreted them, were not in accordance with my prediction. In other words, I thought that it would make it be the case that you don't have the connections with the polarizations that would break up the entangled correlations, but evidently it didn't. Maybe you need something better blocking, something physical, like maybe like rotating like a disc with a small opening or something. Those are also commercially available, but you'd have to have extremely large distances, like almost to the moon. And actually, there's a laser reflector on the moon. Neil Armstrong put one up there. There's some other ones, but I think light would probably be too weak if you tried that. But that's one experiment. A second one, I favored trying the Michelson-Morley experiment on different locations. We're supposed to go back to the moon next year. I'd like to see them try it on the moon, whether I can convince anyone. Actually, my own theory predicts a null effect, and there wouldn't be any change. But some other theories, including Peter Beckman's, that says it is off of the local gravitational field, would predict that there might be an effect, and I think it's probably worth doing. And then one is that experiment that. Okay, excuse me. But my final one was the one that Jean de Clement was talking about. It turns out you can buy like the uh, the tube that he's talking about. He showed me one on eBay for about I think it was around $2,000. I'd be willing to spring for that if it would help actually getting the experiment done. But that would be a third way. So I strongly favor running experiments where they're practical for testing us the implications of different theories. Okay, well, in any event, that's the end of my presentation.
All right. Well, interesting. Um, okay, we're coming up on 4 minutes. Does anybody have any quick questions to ask? No questions.
I don't have a question at this stage, Harry, but just to mention that Jean de Clement gave a talk to the Saturday session in last June, but I think we played a couple of his videos, basically. He seems to be countering not only Einstein, but Maxwell.
Yes. Yes, I do recall that. Interesting. I'm not so sure about yeah. Einstein. I'm sort of don't have much of a disagreement with because, like I said before, my main problem that I ran into with special relativity was this idea that magnetism is a special relativistic effect, and that I couldn't make any hide nor tear. I couldn't understand what that claim was and what it was about. And that started me down this whole route of looking at special relativity and studying what it was about, its mathematics, Lorentz transformations, and all that stuff. So
you don't need any woo-woo for magnetism. It's proven that it's charged particles in motion that creates magnetism.
that's what Jean de Clement, I think, is claiming is incorrect. Is that
So what one could claim it's a relativistic effect in the sense of Galilean relativity, so that if there's a relative motion between, say, a conductor and a magnet, you get an induced EMF. So you don't have to bring in SRT. You just bring in the fact that
Well,
there's
you
of
you don't
motion.
you don't have to use a magnet and a wire or anything like that. Think of it in as it happens in the cosmos when charged particles in a Birkeland current are in motion, they create a magnetic field. You don't need a wire, you don't need anything except for charged particles and their motion to
Yeah,
create
well,
that
that's the same
magnetic
thing.
field.
Charged particles moving are equivalent to a current, and relative motion between that
Yeah.
and a magnetic field gives what you said. Yes.
Okay, but I'm correct in my statement that Jean de Clement disagrees with that, correct? Is that your understanding?
Disagrees with the relativity.
He disagrees with my understanding of his experiment, or what he's trying to do is he claims that the motion of a charged particle doesn't cause the magnetic field, that the magnetic field is intrinsic to the electrons.
Hmm.
Possibly. I'm not quite clear if that's what he was saying, but
All right.
quite possibly that is the case.
That was my understanding of what he's saying. All right, we got
Well,
Anders.
if that's what he's getting at, I think he's on the track of what gravity is, not what magnetism is. The combination of the magnetic moments or electric positive and negative moments of each atom or each um,
We're going to get
electron
cut off here pretty
cause
soon.
that effect.
All right, now we'll talk about this in the next session. We should be ending here pretty soon. We created some controversy in the discussion.
That's good.
I did want to make a few comments. One was every time I see that diagram with the vorticity in it, I think of sunspots on the sun.
Uh-huh.
And it just, the sunspots on the sun, when you go across on one side of the equator in the northern hemisphere, the polarization or the magnetic fields are in one orientation, and in below the equator, they're in another orientation. And every time I see that diagram, that's what I think of.
It's the Coriolis effect. Same with the flow of water on the Earth in the northern hemisphere.
Maybe so. I don't know. What you're welcome to give a presentation about these things, Rick. Um, Tell us about what you think. Um, okay. I guess mentioning Jean de Clement has caused some controversy. I'm not really surprised by that.
Yeah, that's
Uh,
okay. I'm not even sure what I think about him, but he
um,
does have some ideas.
yeah, my understanding is that he thinks that the magnetism is intrinsic to the electron, and it's not necessarily caused by the movement of the electron. And
Yeah, well, he brings in Occam's razor there. He says it's simpler. Why bring in two explanations when just one will do? If you
right,
can get it to work, fine. I'm not sure whether you can.
right. A couple of other things. Once I got into this business of relativity as magnetism is a relativistic effect. That's a bunch of words that don't really mean anything as far as I could see, right? It seems kind of like a vague assertion, but all the textbooks like to say that.
The
And
best explanation I've seen from that is also in the Feynman lectures on physics in volume 2. He goes into it in some detail. I don't agree with him, but in terms of explaining how it would work, that's the best explanation of it I've ever seen.
right, but the issue that I would have is I don't really, since relativity doesn't apply to is basically inertial frames. How does it apply to electrons? I mean, electrons are supposed to be spinning, so it doesn't look to me like special. How do you apply special relativity there? seems to me that's kind of a problem.
But how can you, they also say electrons are point particles. How can you have a point particle spin? It's not clear
Yeah,
to me.
right. Exactly. Um, okay, so I want to beat my little drum a little bit here in that I did do, um, I started off looking into the history of electricity, and what I discovered was that magnetism, the theories of magnetism, as I mentioned previously, go back to the Greek era. Okay, and that the ideas that the Greeks had were pretty well developed. Okay, and they actually what you could call that their theories of magnetism actually existed during the Greek era. That's kind of a stretch to call them theories. Anyway, my point that I'm making is that I wrote up this, written this up, and I was planning on putting out a book on the history of magnetism, but by the time I almost was get ready to get done, a bunch of other books appeared. So, but anyway, you can go look that up. It's at the General Science Journal. There's a series of papers on the history of magnetism. And one of the things in the that I talk about is, and you mentioned this, is this idea of when they discovered this was a big breakthrough when it was discovered that you could magnetize steel, okay, by rubbing or touching and stroking steel bars with a lodestone. And this basically meant that they weren't dependent upon lodestone, which is a magnetite, a mineral. And prior to this, if you wanted to do any experiments or work with magnetism, you had to buy lodestone, okay, which was kind of an expensive mineral because it wasn't very commonly available. Um, and so then it became possible to make magnets, okay, because once you made a magnet by stroking with a lodestone, then you could take the magnet that you'd created by that and make other magnets. And so this basically was a new technology in magnetism. So I think it's interesting that you mentioned that.
Yeah, I do know this. Like people like Thales, my background is philosophy. And so with the pre-Socratic philosophers, typically for what they actually said, it's just a few little fragments. Like Thales said, everything's water. And there were a few other, he supposedly predicted a solar eclipse and a few other things, but he doesn't say very much. And to try to read a theory or anything much, I mean, you also do end up through secondary sources like Aristotle. And Aristotle and Plato, neither one liked the atomic theory or anything. And so they put their own spin on things. But
Right. Well, if you're anybody's interested in this, General Science Journal, Harry Ricker. Okay, and I start off with Thales, and of course, there's really nothing direct from him. It's all Aristotle quoting Thales said this and that sort of thing. But you do get later, after Aristotle, you do get some um, ideas that you could be called a theory, or they're more like explanations when you get into the atomists. Okay, they have this idea that magnetism and electricity are caused by particles that flow out of fluids, and they call them subtle fluids. And anyway, to me, what is kind of how should I put this? It's not when you get to the modern era where they've associated magnetism with spin of atomic particles. That's really where you pick up the story with the Goldschmidt experiment. Okay. And the modern ideas about magnetism are that it basically has to do with the valence electrons and the spin orientation of the valence electrons. And that's what causes material to be magnetized or not magnetized.
And how do
And
they create magnets? Sorry, how do they create magnets today in our time? They put an electric charge through them to charge them, right?
well, they run an electric current and the magnetic field produced by this
Alignment of the atoms.
very high intensity current. I mean, it's like it. I think I'm not sure exactly what they use, but essentially, it's a very high intensity brief current that
Right.
is, and then that's how these. But
That's how they force all the atoms to align within that metal.
that's one theory. Yes, the alignment of the atoms. Yes, that's a theory. Yes, that's the prevailing notion, so to speak.
And I agree with it. I think it's correct. And science gives us good science, and then they give us this relativity nonsense and cosmology nonsense based on gravity alone. And that's what's throwing them off. That everything is collisions and explosions, and gravity is the cause of that. Anyways, carry on.
Okay. All right. Anybody else have any comments? I'm sure Jerry's got lots of questions.
Well, I wrote down some in the chat room.
All right, get up closer to the speaker, to the
Oh,
microphone.
really? Well, I'm sitting in a chair with my laptop. Yesterday on what was it? Well, it was on the actual show, the live show. I could hear myself actually loud on the video. I guess I might have turned the volume down accidentally, or what, didn't turn it up.
Well, we're hearing you good now.
Okay, cool. Alrighty. Well, Bob, I wrote quite a few questions, and
I think it will work best if you just repeat them.
okay. Well, there's quite a few, and I won't go over them all. It's just that this is new territory for me, and I was just asking questions because I didn't realize the complexity of the electron until recently. uh, well, well, let me start out with something that I theorized for quite a few years, that Harry recently introduced me to, the idea that protons and electrons have magnetic moments, which I wasn't aware of. But this is what I wrote. For quite some time, I've had the possibly quite naive theory that protons and electrons correspond to the poles of a magnet. It was pointed out to me that protons and electrons may have magnetic moments, though I haven't studied in detail precisely how this was verified experimentally. Is it all possible that even though protons and electrons may temporarily serve as miniature magnets, they can indeed correspond to the magnetic poles, given that there's a seeming polarity there of the positive and negative charge? I didn't know if that seems plausible at any level.
Okay, so you want to have the electron, let's see, have poles to it, a north pole and a south.
Well,
Well,
for
first
instance,
off,
that the proton may correspond to the north and the electron the south, for instance.
Don't leave out the neutron.
mm, uh, my understanding is individual electrons are said to have magnetic moments. You may very well be right about the proton also having one. I don't know enough.
Okay.
Actually, but yeah, but the rest of it doesn't sound right to me, at least on the surface.
Well, it's only at certain times, though, right? That magnetic moments occur with the electron. So,
Well, the evidence of it, yeah, like with the spin, at least if you're talking about with the Zeeman effect, yeah, you have to have a magnetic field before you have the Zeeman effect,
well,
or the splitting of the spectrum lines.
what if when there isn't a magnetic field? Just say in outer space, objects, the atoms that compose objects in outer space. I mean,
Okay.
uh, if they aren't experiencing magnetic moments, could the protons and electrons possibly correspond to the poles?
Okay. Well, you wouldn't have the Zeeman effect, I suppose, in outer space if there's no magnetic field. If you're right there, maybe
Yeah,
someone
it's
else has a good answer for you on the rest of it.
oh, that's
Here.
cool. I have quite a few other questions that
All right,
may be
Jerry.
obvious. Yeah,
Jerry, I'm not really sure here. Magnetic moment is basically means that it has a magnetic field.
yeah.
Okay, so electrons have a magnetic moment. That means they have a magnetic field because you have a
That they have both
dipole field.
poles, or they have
Yes,
both poles.
yes, you have
Okay.
when you have you can't have a a field without poles.
Yeah,
Okay, that's a characteristic of magnetism.
yeah.
And so if you have a spin means basically the same thing as magnetism. Spin is, I find it very confusing, because I never really understood what they were talking about. So apparently they think that spin it means it's similar to magnetism, I guess. So that an electron spins and therefore it creates a magnetic field, right? So they're deducing the existence of spin from the existence of magnetic field. Does that sound correct?
Yeah. Well, uh, I actually read that protons and electrons experience magnetic moments when I queried Chat GPT. Actually, uh,
Right.
well,
Well, it's kind of a surprise that if you have something that's a point, that it would be spinning and create a magnetic field. Obviously, a point can't do those things. That's why, you know. But
Perhaps it would be worth asking Bob at this point, if I may, what is his view on the existence or otherwise of single magnetic poles? I mean,
Monopoles.
people like Charles Lucas have claimed that magnetic monopoles can exist, and
I've
do
even heard
exist.
of people saying that they've detected them. I would say this. I don't see any good evidence for their existence. And according to, I think it's the fourth Maxwell equation, they can't exist. It's not necessarily that I'm tied to Maxwell's equations, but I don't see any good evidence for their existence. So I think I'll put it that way. And some people say that they can't conceptually exist, and uh, I don't know if I necessarily have a strong opinion on that.
Can't have yin without the yang.
mm,
Yes, yes. I mean, I basically take that as the case from the lack of divergence of the magnetic field. But I think Lucas has mentioned at one or two lectures that fridge magnets are monopoles. He's claimed that.
He may have claimed it, but I wouldn't have a strong opinion on why someone would say that. But I haven't really looked into it either. But
Okay, thank you.
well, I have a quick thought. Well, as far as when you have a magnet and you induce when you induce a current in a wire, that's only one pole that you use, of course. So it affects it creates a current. Like I'm guessing whichever pole that you use. So I mean, I'm trying to figure out what that means exactly. uh, well, um,
well, let me
in
stop you there. That's pretty much got a lot of people puzzled. There's what's called unipolar induction, which is a big mystery that's not solved.
huh, wow. Well, I have a few other questions if that's okay. Let's see. Okay, you mentioned how magnets affect atoms, and you didn't specify metal, and you had said that only with the number of an even number of protons and electrons, which I found interesting. But how does a magnet affect such atoms that aren't metal?
I do know for making magnets, iron seems to be the best element. Cobalt seems to work fairly well, and I think there are a few other ones. And then you get alloys where you get even better magnets. Beyond that, I guess, I mean, you have to bring in like the chemistry of like metals and non-metals a little bit, like valence electrons and things. I I don't know if there's that much more I can really. Someone here may know more than I do on this topic. But let's see. Maybe you can repeat this. I think your question had more than one part.
What, yeah, yeah. Well, specifically, uh, atoms that aren't metal, like, does a magnet affect them?
Okay. Well, what I
Yes.
did. Actually, I remember something else you said, and that was where with with even numbers, there the spins cancel out. Because with an odd number, you either have an extra spin up or an extra spin down. And evidently, for the normal Zeeman effect, there's no splitting for even numbers, which shows that's what Goldsmith and Uhlenbach took as evidence for spin, because they could account for the normal Zeeman effect off of this by bringing in an extra a degree of freedom there.
So magnets cause electrons to spin in a different way than they would as usual.
Uh, that's actually a good question. Whether it's the magnet causing a change in the atom itself or in the light. You're probably right, I would guess. And sometimes I'll admit I'm not always sure of my answers. You're probably right that it's an effect with respect to the atom itself, which would involve the ways in which these vectors align in the presence of an electric field. And I try very hard to be a realist about all of this, which isn't always easy. So I want to be a realist about the existence of these electron orbitals.
Okay, Bob, could you explain what you mean by being a realist? That's a philosophical position.
To hold that something exists. Non-realists, like positivists, they would say physics is a big calculating device for making predictions about observables, and you really press them, and their observables, at least for some of them, turn out to be sensations in the mind. There's a link between positivism and idealism in philosophy. I personally am a dualist. I believe consciousness exists. I actually believe consciousness is spatial. But there's something else that's spatial and temporal, and that's the physical world, which we're never certain about our claims about it. But I do want to make claims about it. I think atoms actually exist. I think electrons do. I think photons do. But the way in which they exist may be quite different from even the way we're taught. That's why you have to work with models, and you never gain certainty there. But if you make a commitment that something exists, then you're a realist. Uh, in mathematics, realists talk about numbers actually existing. I'm not a realist in mathematics. I think there are numerals, but I don't think numbers have an independent existence. But again, working it out, the devil's in the details.
Well, they represent they're a tool to represent if you want to apply them to physical objects, for instance, I'd say.
For numbers,
Yeah.
yeah, it turns out most mathematicians are what they call Platonists. Plato believed in these ideal entities, forms. So Plato would love that the abstract entities exist. I don't see how they can exist. And if you say they don't, which is Aristotle's position, then you're a nominalist.
Hmm. Okay. Well,
Yeah,
With
maybe.
regards to the Zeeman effect, just coming back to that for a moment, um, it has its analog in the Stark effect, which is the
Or
splitting.
the electric field, yeah.
Right, so yes. So therefore, one would infer, I think, would one, that the origin of the two effects would be the same, basically, or very similar.
But one thing about the Stark effect, my understanding is you don't have a splitting of spectral lines, but more like a smearing. It's spread out. Whereas with the Zeeman effect, you still have exact lines with exact positions, except it's just you have more of them. Things split up. And why there's a difference between the electric field and the magnetic field on that, I don't have a good answer. Maybe someone else does.
Could the smearing be caused by the changing orientation of said atom
Hmm. Maybe
due
I
to
don't.
the electric field or magnetic field being applied to it?
Hmm. Maybe.
I haven't come across that personally, but do you know what the conventional explanation is for the smearing, if there is one?
Uh, I could, well, I have the book near me, but I would take a look at that Hertzberg book. He does have a section on the Stark effect and see what maybe he has a bit of an answer there. I don't know off the top of my head.
Bob,
Yes,
I have another question.
sure.
Would you possibly know how the spin of an electron was discovered, that there's spin at all?
I don't know whether you want to say discovered or invented, but
I was going to say theorized, but yeah.
theorized. Okay, but well, there's more than one reason. Like, if you want to have the Pauli exclusion principle, you do have to differentiate between the electrons in a single orbital, and they have different spins. That does it. That would be one reason for conjecturing, at least, that spin exists. And also, as Uhlenbach and Goldsmith explain, you can account for at least the normal Zeeman effect, uh, because whether you have spin up or spin down, that would account for whether you have the higher energy or lower energy with your spectrum lines. I mean, evidently, even in their paper, they say that some other people. You got the paper here.
But spin is a quantum mechanics concept, as I understand it.
But
And
is it the old quantum mechanics or like the more with the Copenhagen interpretation?
right,
It seems to me that they actually came up with it around the time of transition between the two. So I don't know as everyone held the Copenhagen interpretation when they came up with a spin. Goes this paper of theirs. It's back in 1926. And actually, I just looked at it. They mentioned Compton as having had a theory of a spinning electron, which would be even earlier.
right.
I guess
So
it's
the
the same
idea of
Compton of the
spin,
Compton effect.
so the idea of spin is kind of like a physical interpretation of it's a realist concept, basically.
I think they were thinking of something really spinning, and obviously you can have
Right.
clockwise or counterclockwise something really spinning.
And
Uh,
since it's a charged particle, that would produce a magnetic field.
mhm.
That's my understanding of it. And
Yeah, and of
and
course,
then if you have right, and then if you have a magnetic field, then you would have a magnetic moment, okay, which is a vector concept,
right.
okay, related to the dipole field of a magnet. And that is when you have like a magnetic dipole field, then you can manipulate the electrons with magnetic fields, which is what Uhlenbeck and Goldsmith are doing.
Well, at least explaining. I don't know as either one was an experimentalist, but I don't know enough about them.
well, now this is the experiment with the gold silver atoms that they're talking about, or is this a theory?
Let's see. Their diagram. Oh, let's see. I got the paper right here. It has a.
Well, my understanding is there's this experiment that's done with silver atoms where they um, have a beam of atoms that goes down
Okay,
through
no, I know. I
space.
can. I'm trying to remember the name for that experiment. Maybe someone else can help me out here. So
CERN Gerlach.
you
CERN Gerlach.
You're right,
Stern-Gerlach.
Stern-Gerlach. Yeah.
Okay. Okay. All right. So the Stern-Gerlach experiment is the experiment where they determine that this spin exists.
Yeah, okay. Do you know the date on that experiment? Because they don't mention that one.
Is there any detail of how, like why they think that though? Why they observe spin?
Well, here it separates your atomic beams with the Stern-Gerlach experiment, and they explain that in terms of spin. That part's true. I was wondering maybe someone can do a Google search on when the experiment was done first.
Well, what happens
1920s.
in the
I don't know.
what happens in the
1920 what?
experiment? Excuse me. What happens in that experiment is that supposedly you can separate up and down spin into separate beams.
Right.
Then, if you take the beam which we say is the upspin beam and subject it to the same magnetic field again, passing through, let's say, a second Stern-Gerlach experiment, it also splits into up and down,
Right.
which indicates that it's actually not a property, the up and downness, if you will, is not actually a property of the particles themselves, but rather the environment in which they're passing through.
Yeah, you can do the same thing with light. You can do like polarizers, and then you put a third polarizer. You say do it the first, like either horizontal or vertical, and then you do another one at a different angle in between, and you get the same effect. Uh, as for what lessons to learn,
But does
I
that
don't know
mean
if
that if
everyone
you
agrees
just
about
take
the
a
lessons.
polarized beam, that you can get the two angles again, or the two polarizations again, if you pass it, through your filters?
Through a
I
third
have
one,
a,
yeah, light. You can
Because
have
that's what's
zero light
happening with
after the,
Stern-Gerlach.
yeah.
I, have you got the name for that experiment? Because I haven't heard that one about light.
Let's see.
Stern-Gerlach was 1922, by the
No,
way.
no, not Stern-Gerlach, the one he's talking about where you can actually flip the polarization of light.
I don't have it right off the top of my head. I do know where you put a horizontal polarizer and then a vertical one, and there's no light after that because the effects cancel out. And then in between the two, you put one at a different angle, and you do get light after the third one then. I don't have the reference right off the top of my head, though.
Okay, I think I know. I think I might have seen something along that lines. I was going to ask a question. I only got a short time because I'm kind of in the middle of traveling here. So I was going to ask: does anybody understand why there is the right hand rule exists? I mean, it's a rule, but it's a physical rule. Every time you move a charged particle, you get a magnetic field always in the same direction.
Someone have a good
Well,
answer for that?
Harry's an electrical engineer, so he might be able to explain that. But yeah,
But he's asked this is kind of this issue about chirality is really what he's asking about, and I'm not really that familiar with whether or not anybody's tried to explain why the right hand rule exists. Why would that exist? It's an experimental fact, basically, and I don't
And
know
you
that
have the right hand rule, which is supplemented by the left hand rule, which is basically a consequence of Lenz's law.
Yeah, but every time you move an electron, if you move it away from you, the magnetic field is always going to be a clockwise field around it. And if you move, so it's like regardless of it's always going to be right hand. Now, my model has an extra explanation to that, and it does use sterility, as Harry says, basically, because basically the electron doesn't just spin, but it also rotates simultaneously. And if you spin clockwise and you also have to rotate clockwise, then you've got sterility in the electron. But if you spin an electron simply in a plane or simply in one direction, you can just turn around and look at that electron coming at you, and instead of going clockwise, it's going to be counterclockwise. So the only way you can get it so that it goes away from you and it's always going to give you a clockwise magnetic field is if it has sterility built into it. That's my thought on it. Anyway, I do have to go. I'm sorry. I'll listen to the recordings later. It's really good and interesting talk. And thank you very much, Bob. I appreciate it.
Sure.
I will definitely look forward to looking at the recordings later because I haven't been able to pay attention to the whole thing.
Feel free to email me also.
Okay, great. Thanks.
Okay, sure.
Bye-bye.
I'd like to ask Bob.
The chirality has been built into our mathematics because it's a fact of nature. So say V cross B is the turning of a right hand screw.
Yeah.
So we B cross V would be the other way around. It would be going out the other way.
Yeah, I'm not really familiar with this topic. We only have a few minutes left. And I think there was a thought that this chirality was a law, an absolute law of nature until they found there were some violations of it. There were some left-handed.
There was an experiment. I think maybe at Brookhaven. I forget the people. Maybe someone remembers saying that there was a violation, parity. I think, in violation of parity.
Right. Okay, that's kind of a different topic, though. I think.
Yeah.
All right. So we've covered a lot of time here. We got 5 minutes. Any further questions? I'm sure Jerry has more questions.
We'll have a few more. Well, it's sort of an offhanded thing. It's something you had suggested though that electrons aren't point particles. How would you define a point particle?
The concept came from Boscovich, and it just doesn't have any size. Kant also, the philosopher Immanuel Kant, he also talks about basically, well, he has fields of force, but there's no, the center is just a point. It doesn't have extension. So it's an old concept, but they seem to love it with modern quantum mechanics, and people in special relativity seem to love it.
Well, in quantum mechanics, particles can jump in and out of existence and such. But well, then again, when they exist, aren't they like somewhat excitations within a given field, for instance? However, though, particles that compose atoms are more permanent.
Some are, I mean, now a neutron's interesting because a neutron in a nucleus is permanent, but like a free neutron, I think in 10 minutes or something, it decays. But protons, even free protons or free electrons, as far as I know, that they at least don't decay. An electron doesn't seem to be composite. A neutron is, as far as I can see, composed of a proton and an electron.
Well, if a point particle doesn't have mass, it wouldn't seem.
Who said it? Who said it doesn't have mass?
Oh, well, you might have said something different. So, excuse me there. What did you say?
Yeah. I didn't say it didn't have mass, and I didn't say it didn't have charge. It just doesn't have extension. It doesn't take up space.
Oh, really?
A point particle in my view is just the center of a pattern of waves. So it doesn't have the specific dimension, but just like Bob mentioned, basically you have the spherical wave, oscillating spherical spherical pattern. I think you said that, Bob, I believe, and then you have the rotational pattern around that gives you the charge, the electron type charge. So we call it a point particle because we just idealize all its properties to the center. So that's where we think its location is, but it's really a pattern of waves. That's how quantum mechanics looks at it as well.
That's Boscovich's idea. That comes from Boscovich.
Yeah,
So,
he's one of the ones
Well,
that first mentioned that type of thing, and he didn't get into any specifics of that model, but that's the
correct.
concept too. That was just, and that's basically the way that current quantum mechanics looks at it. Is it's a pattern of waves.
Right.
And
What
Bob,
kind of waves? Because they have probability waves, and there you lose your realism.
Yeah, right. What
Bob,
does it mean?
uh,
yeah,
Wave?
that gets
I have a question, Bob.
All right, we're hold on. We got less than a minute
Okay.
here. All right, go ahead, ask your question, and
Oh, okay, okay. Okay. Would you say that any point particles exist? Because if they don't have mass, if they have mass and they don't exist in space, where would they exist? I mean,
Oh, you can
are
have
they
a point in
theoretical?
space without having extension. I guess that's what they would answer you.
Okay.
well, you get to the Boscovic answer,
Well,
which is that there's phenomenon that exists around the point.
Yeah.
A lot of this
so,
is
so,
based on Euclidean geometry. I mean, Euclid postulated a point which has no extension, but it has existence in space.
Yeah.
Right. All right, we're going to end here pretty quickly. So I think we've got an interesting topic that we can continue on with.
Yeah.
So it says less than a minute here. Well, Bob, you certainly have created a lot of conversation.
That's good.
look forward to the next session.
Okay.
Some of this health stuff. So we went out there.
Okay. All right, we got the recording going here. Roger is here, and I'm surprised he hasn't come in to talk about Boscovic. Roger did a translation of Boscovic's theoretical, I can't remember the name of the book, but anyway, it was one of his books from Latin. And I did a introduction to that, and Boscovic. I have a number of books on Boscovic. He's a very interesting fellow, and I'm not sure if Roger wants to comment on this or not, but certainly an interesting topic. I would think that Bob, you're basically your background is philosophy.
That's right.
Could you tell us about your academic background just a little bit? Remind people.
Okay. Well, my undergraduate degree was from Dartmouth College. And actually, I did a foreign study program at the University of Edinburgh then. And I have a PhD from Boston University. One of my PhD advisors, he was also in the physics department. That's Abner Shimoni. And the reason you might have heard of him is like with this entanglement, the inequality they always test is the CHSH inequality and not Bell's theorem. And the S in that inequality is Shimoni. Uh, so, but I actually did my thesis on the geometry of visual space, which is the geometry of our visual experience. But I think geometry has been sort of my strong suit. And I know, like above Plato's Academy, it says, "Don't enter unless you first studied geometry." Uh, so, but that's my academic background. I've taught at various schools, but I'm retired now.
What have
Okay,
you
and
taught? I'm sorry.
yes, tell us where you
What have
taught.
you? Oh, okay.
Bob, tell us where you've taught and what subjects you teach.
Okay, let's see. I've taught a variety. Let's see.
Mostly philosophy, correct?
Introduction to philosophy, logic. I've taught philosophy of mind. I've taught philosophy of science twice. Once at Boston University, once at Wayne State University in Detroit. I've taught at various community colleges. I taught Oh, the Lutheran school, Augustana. I taught, let's see, a year at Ohio Wesleyan University. It's been kind of checkered. I never really had a good tenured track position, and done a lot of adjunct teaching. Some's been full time. I was full time one semester at Central Michigan University. I don't know. I find the field it it's a field that's interesting, qualities all over the board, but you can't really duck it if you're going to get into some of the topics that you're talking about here.
Okay. On the issue of Boscovich, okay, which I think is an interesting, would you consider him to be, he doesn't come across to me as a realist according to your definition. Where would you put him in the philosophical spectrum?
I've read a book by him. I think you're right that the original was from Latin. Uh, I think he's a bit of a medievalist. You're almost better off doing a Google search on his actual positions. There were a lot of people in medieval philosophy who kind of took a religious outlook, and the Catholics, they tend to be Aristotelians, and you're better off with a Google search for more information on him. I can't spell it off the top of my head.
Well, he was
I
a
know he dates back
Jesuit.
quite a ways.
He was a Jesuit, and
Oh, Jesuits, Catholic.
yes, exactly. Yes, exactly. And he was a follower of Newton. He was a big proponent of Newton's theories. And but this idea of the point particle, you have this point, and there's forces around. There's a sort of imaginary forces around the point. So the point's not really a real thing, but the forces are. Yeah, that would be my understanding of it.
Yeah, and I know Immanuel Kant, who's also a philosopher, said something quite similar. It turns out Kant, he also worked in astronomy besides philosophy. He had a theory of planetary nebulae, among other things.
Okay, now to return to the main, Jerry, do you have any more questions? You seem to be a font of questions.
Oh well, I had quite a few on the side that I didn't get to that I didn't reprint. So, well, one quick point about point particles again. Uh, well, does a point particle exist as empty space? Yet surrounding it is where it all is. And it's described as having no mass because what it consists of, or it indirectly consists of what surrounds it, I guess.
I
Like
guess.
is empty space.
Yeah, well, I do know this. I don't know if this helps, but do you know the Dirac delta function?
Oh, I don't.
Okay. Well, it integrates to one, but it's supposed to have one specific location. And now you can have something integrate to one at one point. I mean, some people say it's an illegitimate function, but they use it all the time in quantum mechanics. Uh, and you can do like approximation functions to it, in which I suppose I forget who was talking about the summation of waves. So like yeah, or like with the Fourier analysis, for example, you have a summation of waves, and you get something kind of different result. You have something like a square and things as a result of the summations of these waves. Uh, so yeah, I suppose that's one way of looking at it as the result of something like an approximation function.
Wow.
And the people who object to it are the mathematicians because
Some of the mathematicians, some mathematicians don't care, but
okay. Oh, okay.
We're talking about the Dirac delta function. We use that in electrical engineering. That's usually taken to be an approximation of an impulse, meaning a short transient signal. So you get like a very short transient signal, and that's treated as a Dirac impulse function because technically it has zero width, so therefore it can't have any energy. Okay, because it's infinitely small, so you can't integrate it and get any energy. But supposedly it's defined in such a way that it has energy, although it has zero width. That's what you were talking about.
Right.
Okay. And I guess we're sort of in this business of point particles, but I think didn't James Arathun that was Saturday before yesterday was talking about a model of the electron where he was visualizing it as a torus, and torus models of the electron have become fairly popular in recent years, I think.
Yeah, there are all sorts of models out there. I don't know if anyone who takes my move is spreading it out over a whole orbital, but there are all sorts of models out there. So they don't all say point particles.
I have a question for Bob. Um, well, first, thanks for a great presentation, man. That's been very, very interesting. Um, I understand in your slides you assert that the electron could have a clockwise and or a counterclockwise spin. Did I get that correct?
Uh, for an electron pair, yeah.
For an electron pair?
For an electron pair, it works out best, really, because for an electron pair, one spin up and one spin down. Now,
Okay, with reference to what is my second question? Because like if we change our position, wouldn't the counterclockwise spin then be considered to be a clockwise spin? And in other words, what is your reference frame for asserting that there are two different opposite spins?
okay, well, spin, you're talking rotation. For rotations, there's an absolute uh, reference frame of rotation. Newton knew this like with his water bucket experiment. You can show this like with the Foucault pendulum, which shows the rotation of the Earth. So where the Foucault pendulum isn't rotating, that's your absolute rate of rotation, as far as I can see, for the whole universe. There's no primitive like rectilinear motion, but there is for rotation. If that's the case, then you can talk about your spin with respect to that absolute rate of rotation.
So you are then in support of an absolute reference frame. Thank
For
you.
rotation, but just
for
for rotation.
now, why would rectilinear motion not be included there? If I may continue this line of questioning, if I may.
Okay, I don't see it. There's any good evidence for it with respect to, I mean, there are any number of experiments like on a train, you play ping pong, you can play it on a moving train and things like this. So the laws of physics remain the same. The train goes around a corner and it's really going to mess up your ping pong game. But there you're introducing rotation.
If it goes back to sterility, then as you're basically referencing the spin to the rotation of the spin, and that can only be in one direction, left to right. If you're looking at something, if you're looking at a clock and that clock is going clockwise, you can look at the backside and it's going counterclockwise. But if you look at a clock that is not only rotating normally, but also then spinning, looking from the top or bottom, also spinning, then you have a reference of spin, because you could have that clock either spin counterclockwise when you're looking at it, meaning this, like the 3 is coming towards you and the 9 is going away, or you can have it going clockwise and the 3 is going away from you and the 9 is coming towards you. That is unique to sterility. So that gives you a reference of direction of spin.
And on a larger scale,
with nothing else to reference it to except for that particular particle pattern.
and on a larger scale, if you're talking about a planet, if it flipped, if it did a 180-degree flip where the North Pole and South Pole exchanged, that angular momentum would be non or insequential. There wouldn't be any devastation on the planet because it's all being changed at the same time. But
Right, well, and there is no sterility. Still, there is no sterility. So, like I said, if you look from the North Pole down, you see a counterclockwise rotation. If you look at the South Pole up, you see a clockwise rotation. But if you don't have a planet or something else to reference to that too, you don't know which way it's going.
yeah,
It's got to have some sterility to it.
Yeah. Or helicity, I guess is another term. Here's an interesting one. I don't know if this one's from Kant. The left-hand glove and the right-hand glove, you can't have the same space. You can't make them overlap. And he took that as evidence that there's no physical space apart from our experiences. He says it's just for the experiences, but I don't think I agree with him there. But he is right. Some things you can't make overlap, even though internally they have the exact same structure.
Bob,
Yeah,
when you spoke of electron pairs, you
yeah,
meant did you mean two? You meant two electrons?
yeah. Like in an orbit, you can have
Oh,
like, two
how
electrons.
common is that?
Very always.
Oh,
Well,
wow.
here's what for even numbered electrons.
Really?
Uh,
Like even
okay.
within an atomic system?
Yeah, an atomic system. It always
Really?
does, but you can sometimes have an extra one, and that one isn't in a pair. So
So
that's the difference between your
one of
even
them
numbered
spins.
elements and your odd numbered elements.
So one of them spins one way and the other spins the other way.
And within the orbit, yes.
Oh, well, I thought you meant in the diagram. I thought you meant that at the top it spins one way and then at the base it spins the other way.
Yeah, and that ties in again with my model. So
Oh,
with my model with like an orbit with two electrons, I guess putting them at somewhat different locations, one above the equator and one below the equator.
well, I mean, like an electron doesn't physically spin, does it? Is that sort of like an analogy, or
Well,
is it?
it's spinning in my sense. You have these eddies, and then you have a maximum at the North Pole or the South Pole.
So what would go on at the equator, though?
Uh, Nothing. I mean, no spinning. But again,
Oh,
that's just one it doesn't have any dimensions to it. It has no size. So above it, everything's going clockwise, and below it, everything's going counterclockwise. But it's the dividing line, sort of a neutral dividing line.
well,
Bob, are you saying, Bob, that as we move from the equator in your diagram up to the pole, the amount of spin is changing? Should we take that away from your analysis, sir?
You got to be careful with an answer. You really do, because spin is quantized. Like they do it like in terms of half integers, one half or minus one half. And I don't know if I have a good answer thought out beyond that. I just know you have to be real careful with what you say because it's quantized. So you want to have answers that come out quantized.
well, what is meant by quantized with this example exactly?
Like spin one half or spin minus one half, okay? You have exact numbers there. And those are your only two choices for spin, which when they call them spin up and spin down.
And there's also
There seems
particles which have spin one, plus or minus
That's
one.
right. There are, but the electrons just spin one half.
there
Maybe,
seems to be a preponderance of right-handedness in the universe. Now, for example, the DNA structure, the double helix, is right-handed. Now, maybe there's some fundamental physical reason for this,
there
or
may be.
a bias of our own human nature, which is largely right-handed, that's imposed this upon our thinking. I don't know what you think of.
Well, on this, apparently they manufactured DNA with left-hand orientation. I was surprised when I heard this. So normally DNA has a right-hand structure orientation, but they managed to create a left-handed oriented DNA or protein, basically.
Does it work? Does it work? Like what?
Well, I guess so the speculation is what happens if an organism with left-handed DNA escapes the laboratory.
Well, it's a good question.
Yeah, well, the
It's
answer
like
is
matter and antimatter. It's the
the
opposite.
answer is that there's no left-handed DNA organisms for it to eat, so it can't survive. Anyway, yeah, that's interesting that you bring that up, Ian. That there is that orientation does exist in DNA, and all of the animals that we know of have right-hand DNA proteins.
And indeed, Harry, is it just a chance, a 50-50 chance that nature's gone this way and it's propagated that way? It's a stable situation, or is there some more fundamental underlying reason that we haven't fathomed yet?
I think that's a question to ask the philosopher Bob
Yes.
Bob French.
Yeah, I don't know.
Bob, have you considered the so-called distinction between fermions and bosons with respect to spin, the former being 1/2 plus or minus, and the latter, such as the photon, being spin 1?
Well,
Has that figured in your analysis at all, sir?
well, one point you can make is the Pauli exclusion principle. It just applies to fermions and not to bosons. So you can have like photons are bosons, so you can have more than one in the exact same state. Uh, I know I've heard about like helium, maybe really cold, so you get connections there with like a superconductivity and stuff. And again, I'm not really an expert in this. The real truth is you can't be an expert in everything. There's just too much to know. Uh, but I do know that there is the difference in whether the Pauli exclusion principle applies or not.
Um, does every particle spin?
Uh, Good question.
I think it's intrinsic.
You're probably right.
Right-hand rule of electrical force
Well,
applies
I mean,
all the way down to the atom.
I mean, I'm personally skeptical of the existence of photons, for instance. As far as the particle wave duality and such.
Oh, my answer there is I hold wave particle unity. So I think they both
How
exist
does that
as
work?
wave packets.
How does that work?
You have a wave packet. My version of it, it just has light at one particular frequency within it. So it has a finite emission time. And it spreads out. It spreads out as a spherical wave. But within the wave packet, there you have oscillating transverse waves. So it's not, actually, you can even show wave properties and particle properties in the same experiment with the same light. So a lot of the claims which they made for the duality just don't hold up. It's just they made them so long ago that they got stuck in the physics. They got stuck in the mathematics of the physics.
Yeah.
Like with Heisenberg, which also there are exceptions of the Heisenberg uncertainty principle. They talk about non-commuting operators. And it turns out there you can have more precision than is allowed for both position and momentum with the same particle. So a lot of this doesn't hold up. I can give references for experimental counterexamples to almost all of these principles, but they got stuck in the textbooks.
All right. Don't want to change the textbooks.
I don't know.
Well,
Okay, I'd like to go back to Jerry. Go ahead. What's your question?
okay, just real quick. With the photoelectric effect,
Yeah.
it was supposedly demonstrated by a metal plate, some type of metal with a certain type of frequency of light shown on there that would cause electrons to jump out of the plate. That I mean that the photons would hit, or the light particles would hit and collide and cause them to jump out. That doesn't necessarily mean that light consists of a particle. I wouldn't think.
Yeah,
Only
you're right. You're absolutely right.
that
What
light
it
affects
shows is
particles that way.
Yeah, what it shows is absorption is quantized. It doesn't mean that each photon or source came from the same place. It just means that a discrete amount of energy was absorbed. It doesn't say where it came from. But my model of these wave packets is I think they get split up and recombined from different sources all the time. So I agree with Feynman that light takes, he says, all possible paths, including real crazy ones. I think you just need the sane paths, the ones with which are physically possible. But the effects like reflection, it occurs at very low intensities of light. So I don't see how you can model that with saying that the photons are absorbed and re-emitted light from the each part of a mirror, for example, because you can get a mirror image even at very low intensities.
Yeah. Well, I mean, did you mean that that light doesn't travel in one direction? I mean, if there's just like a star, it shines into all directions, of course. But
Well,
if
I think from an
directed,
atom it goes in all directions.
oh, okay.
It goes as a spherical wave. But then you have what's known as the Renninger effect. So if there's a possible absorber and it doesn't absorb, it's like it pushes things to the side. Or if there's absorption when it doesn't absorb, so you get shadows and things. So what started out as a spherical wave in all directions, when something doesn't happen, it makes some of those directions, the light no longer goes past an object,
Oh,
like
yeah.
with a shadow. Uh, so yeah, and eventually it can be very tightly constrained. But even a laser beam spreads out a little bit more than people realize.
Well, I don't really know about laser beams, how they work, but it seems that most light sources propagate into every direction, even like a spotlight.
No, they have a preferred direction. They take a preferred direction, but I think that
Lasers.
light moves as like in a Newton's cradle, but with a wave motion.
Hmm.
Okay, I wanted to go back to the question that we talked about earlier, and that is about metals and magnetism in metals. There are three, usually talk about three types of magnetism. There's ferromagnetism, which is associated with uh, iron, and then there's paramagnetism, which has opposite, well, is similar to ferromagnetism, but it's weaker. And then there's diamagnetism, which is an opposing magnetic effect. And what's interesting is that diamagnetism is superconductivity. So superconductivity involves diamagnetism, where the magnet is repulsed from the material that's superconducting. And in ferromagnetism, you have that the magnet is attracted to the material. And I'm not really sure exactly what the explanation for that is. Do you have some thoughts on that, Robert?
You probably know better than I do on that one, Harry. There's got to be something about iron and the electronic structure that explains it. I I don't really have a good answer, no.
The ability
Well,
of iron to realign its atoms in alignment to each other, the crystalline structure, is the reason why iron is able to be magnetized so well. The the rubbing of a magnet on that iron realigns those atoms with each other to create a magnet. A weaker
So,
magnet, obviously, but it still creates a magnet.
so Rick, do you have some idea as to why superconductivity is repulsive?
Well, if magnetism is akin to the electric force, we know that in at great distance, the electric force attracts, and due to objects' individual charges, when that attraction becomes at proximity, when they get close together, it separates. It wants to repel at that point. That's the electric force. And magnetism is akin to it, so I don't see why magnetism wouldn't repel in certain situations.
Well, we know it does. That's the whole. My question to Bob is I think I've asked this question before. Have you put any thought into using your model to explain these differences?
Oh, you mean like
Well,
attraction repulsion?
well, in the case of one case, in the case of ferromagnetism, you have attractive force, which is specific to iron. But if you have a superconducting material, okay, it's not an attractive force; it's a repulsive force.
What creates the
Yeah,
conditions
okay. The answer is I don't, Harry. I wasn't even aware of that for superconductivity.
Yeah, well, I guess what I'm suggesting is it might be interesting for you to take a look at that.
You're probably right. Yeah, there's a lot to look at, but yeah.
Well, I was just curious, what causes the conditions of superconductivity? Like, when is that present?
When
Um, Good question. I don't think they know. They have a theory about it.
Hmm. Yeah.
yeah, you usually have to make something pretty cold, but they found you could raise the temperature for some superconducting materials. But
Yeah, it's a kind of the
They're
idea.
on.
I think the current idea is this Cooper pair theory, that electrons get paired up and then they move as a pair, in a coherent manner, and therefore, because they're moving as a pair in a coherent manner, there's no dissipative loss. There's no the current thinking about current flow is that electrons flow through wires kind of through the lattice of the atoms. And then when you get these Cooper pairs, there's no collisions with the atoms or whatever. There's no friction of the movement. That's kind of my vague understanding of it. I actually don't really think I can understand it. That's why I want Bob to do a theory of it, because I'm not really
I've
with.
I've
For
heard
your
the
information,
explanation. Sorry,
um,
sorry, Ian.
sorry,
I've heard that there's a new explanation of how electrons move, not through the wire, but along the outside of the wire.
yeah, well, that's a skin effect or something. But
Hmm.
I was going to inform you that Stefan Gift, who's talked to us a number of times on various subjects, will has his own theory of superconductivity, and he'll be giving us a talk in some weeks' time on the Saturday sessions.
I didn't know that he was interested in that topic.
No, neither
Okay.
did I. He has one or two things I've been talking to him about, and that's one. The other is I think he has his own gravitational theory, Harry, which we may
Okay.
hear from him later.
Well, as far as what Rick brought up, I, I, I had a skepticism towards the idea that the particles actually travel outside of the metal wire. I looked it up and it says it doesn't, though I don't know how, I mean, Chat GPT and Google aren't always reliable. So I admit I don't know.
Well, Ian was talking about the skin effect. The skin effect only happens when you raise the frequency of an electric charge. Um, you say a million cycles or a half, 100,000 cycles per second, then electricity flows across the body on your skin. It doesn't penetrate into your body and give you a heart attack and kill you.
Yeah. Well,
That's how Tesla could stand in his electric fields and not be harmed,
yeah.
because he had increased the frequency of the electric discharge itself. Now
Well,
So
I
this is
submit.
well known and used indeed in electrical engineering and so on. But I think, Jerry, correct me if I'm wrong, you may have been referring to a more fundamental difference where they're saying current doesn't flow in a conductor at all. It's flowing, it's being transmitted outside,
I have heard that. I'm skeptical though.
akin to the cat type theories, which
That's what
have,
I have heard too.
yes.
Some comment.
Personally, I think it
I'm
might be
tired already
anti-union,
of
but I
this
don't think it's
talk.
absolute. Sorry.
Let me
Okay,
do
so
a couple comments. First of all, electrons belongs to metals. Forget about it. There are no electrons outside. Outside electromagnetic field, we have this combination electrons inside and electromagnetic waves outside of the wire. That's it, simple like this. Don't invent these electrons outside. It's absolutely wrong. And what is important, even our alternative current, it's going back and forth, back and forth. If this electrons going back and forth, how you can transmit your electrical current? How? It's electromagnetic radiation only. What we have going around this wire filled with electrons. Sorry, guys.
Well, I'm
It's
I'm I'm
it
I'm
is
so
well
I'm
known
sorry.
effect for electromagnetic radiation, electromagnetic waves.
I'm sorry, Vlad. There's such a thing as free electrons on this planet, and it's well known that the tips of trees are charged differently than the trunks of the trees and the limbs of the trees. It's
What is
there are
connection
free
to the wires?
electrons
Let me
everywhere.
ask you the question. Please continue in the right way. You are talking about wires and electromagnetic radiation waves around wires. That's it. Forget about these plans, about something else. Don't mix it. Please
I think you mean they're
concentrate on
It,
parallel.
one
it, it,
issue.
it's intrinsic to the universe that there are free electrons and that they do what they do. I mean, it's intrinsic to
okay,
the universe.
We
okay.
have our
We're coming up
electricity
to
at
the end.
home. Explain me why it goes. With alternative current. Explain me how electrons move back and forth, and nevertheless you have your lamp and you
We
have
have
your
a
light right now.
we have electric currents underground, Vladimir.
My goodness,
All
then
right.
why
Telluric
we need all this
currents.
wires side? Why we need to
We
put all
do,
this,
do we Are there
electrical
wires
system?
are there wires underground? No, we have telluric currents underground that are proven fact,
Okay.
All
and
right.
that's
Let me
Maybe
free
let me
Vlad could
electrons
interrupt.
moving.
maybe
Let,
Vlad
let
could
me
look up
interrupt.
the cathode ray tube.
All right. Let me interrupt here. We only got a short period of time. I'd like for Bob to sort of, if he has some comments he'd like to make to finish up here.
Yes,
I don't know
yes,
so
James.
much a summary, but if anyone has an interest, like corresponding with me, I would suggest like doing it by email. My email is Robert period E period French at gmail.com, and take a look at my ebook, A Model of the Physical World. And again, you can get that at www.quantumrealism.net, because I would like to get input from more people. I think there's a lot to be said for collaborative work when people can agree enough about so that it's productive. When you just have different theories and people just, give their different theories, progress isn't made. So there is a lot to be said for if there's some common interest to try to do collaborative work. Okay.
I
Well,
think
one thing about dissonance is it seems to be we are dissonant about everything.
Yeah.
Oh, yeah.
Yeah.
Oh, yeah.
a positive contribution that Robert has brought to us today, I think, is being careful as to what we conclude and what exactly the evidence is for what we conclude. In other words, sort of a sharpening of the intellectual tools that we have. And I think Robert has done a wonderful contribution in that direction. And thank you, Robert.
Okay. Yeah. Thanks to everyone. But yeah. Okay.
All right, we got less than a minute. Anybody else want to make any comments? Thank you, Rob. Bob, I think you're making, I think from, what we've started off with maybe a year or two ago. I can't recall how long it is now that we first started talking about your idea. And it seems like you're getting more clarity to what you're in your model, I think.
Yeah, to some extent. Yeah. Yeah. It comes in spurts. Sometimes big
All right.
ones, sometimes small ones. Yeah.
All right. Well, thank you.
Okay. Yeah. Yeah.
All right. Well, it'll shut off here in a minute. So, okay. Thank you.
Yep.
And
Thanks, everyone.
see you guys
Yep.
next week.